All right, going to have your homework handouts out, and the first problem on the handouts you see up here, we're going to look at that in just a moment. Before we do, let's go and review some things we talked about in our last lesson, and we did have a 3-day weekend, so a little bit of an extended break. We'll see what these students remember coming off that break, but if they seem slow and sluggish, it's because they got extra sleep. I don't know either. Anyway, so we've been talking about different forces that can act on a body. And we've said that as we look at this object, we're going to draw it, class, as the object itself is going to be a box or a dot, okay? And then all the forces that act on the object we're going to draw as arrows because they are vectors. And so this sketch, or this picture, if you will, it's not much of a picture, but this sketch that shows the object and all forces acting on it is called a free body diagram. There we go. The picture itself is called a free body diagram. And what are some of the different forces that we'll deal with in a free body diagram? Audrey?
Applied force.
Okay, the applied force first of all. Now, the applied force, remember, could be just straight on, or it could be at an angle. If the applied force is angled, we've got to break it down into its two components, class. X and Y, right? Those are always your components of different things, X and Y. And so if the applied force comes down at an angle or is up at an angle or something, you've got to break it into its two components. But the applied force, good. It's what triggers the motion to occur.
Normal force.
The normal force, how does that act? Specifically?
And parallel.
Not parallel. Perpendicularly upward. There we go. So upward perpendicular to the surface. Now, so far our surface has always been level. So straight up has been normal. But here at the end of the hour, if we have time, we got a little bit of a delayed start today, but we're going to go to an angled surface. So it's not straight up anymore, it's perpendicular up to that surface. Another force. Weight, which always acts
downward.
Straight down. Now, obviously if the surface is level, straight down is going to be perpendicular. If it's angled, straight down isn't going to be perpendicular, but weight is always straight down from the object. Another force.
Friction.
How does friction always work?
Reverse of applied force.
Good, it's always against the applied force. It always goes against the motion. So we could say friction is always negative. I just always think I subtract the friction. Either way works, though. It's always against, and it's going to be along the surface, right? So if the surface is level, friction is level. If the surface is angled, friction is angled, because friction always goes along the surface. I think we've got one more that we haven't used yet in a problem, but we've talked about it.
Tension force.
Tension force. How would tension force be applied?
Like a rope or something.
There we go. You'd have to have some kind of rope or connector of some kind, chain, string, whatever, that you're pulling on, or that there's a force applied through that transmits through that connector. We said if we took all the forces then and we boiled them all down and we got one single force that showed the outcome, class, we call that the resultant. Do you remember another name I gave the resultant? It wasn't a name for the vector necessarily, but I called it the net force. The net force, the resultant force, the net force, the sum of the forces in the x, because we noted, by the way, that the y is always going to, the y component's always going to cancel, right? You're not going to get, the object sinking into the ground, at least not in our problems, we're not going to see that, or rising up off the surface or anything like that. Now, if the forces do cancel, we have something called, two words, translational equilibrium. If all the forces in the x or all the forces in the y, which in the y they will, cancel, translational equilibrium, which means you will not have any, not necessarily so, acceleration. So for instance, remember we gave the example, if Michael's already walking down the hall and at the same time somebody shoves him from behind and shoves him from the front with the same amount of force, well, they're canceling each other out, but they're not necessarily canceling Michael out. So if Michael was already moving forward with whatever speed, he will continue at that speed. There won't be acceleration, but he may continue moving at a constant speed. We said that the single force that is equal in magnitude to the resultant, but acting opposite in direction, is called the equilibrant. It cancels everything out, right? If the resultant shows the outcome of all the forces, it is the net force, then the equilibrant would be the opposite. It would produce that equilibrium because it would cancel with the resultant. All right, I think that pretty much wraps up our terms that we've talked about in this chapter. Let's go ahead and look at the first problem. You can look at it on your homework handout. In fact, hold those homework handouts up if you would, please, so that I can see they are completed. Excellent. And go ahead and read that problem, either off the screen or off your handout. Doesn't really matter which. Kendall?
A man drives a 15 kilogram desk across the floor with a horizontal force of 55 newtons if the coefficient of friction is 0.341 and the acceleration of the desk.
All right, so for starters here, Kendall, we've got to draw the desk as a box, okay? And the upside of a box is you can write information inside it. There is some information I'd like to write inside, Kendall. I'd like to write the mass.
15 kilograms.
Just so we don't forget, it's a 15 kilogram desk. That's an important number for us. Now, there are several forces in play, Kendall. First of all,
Weight.
I always like to start with the weight. I know it's going to act straight down, so it's very predictable. And I always find weight the same way, class.
9.8 times that.
Right, mass times gravity. Take the mass, the 15 times the 9.8 gravity, and what did you get for the weight on your free body diagram here, Kendall?
147 newtons.
147 newtons. Now, countering the weight, class, we have the normal force. Question, does the normal force always equal the weight? No, remember we used the example if we were to pull the desk. If I'm lifting upwards slightly, I'm decreasing the needed normal force. And if I'm pushing down slightly, I'm adding to the needed normal force, correct? Well, in this case, let's look at the applied force. How was the force applied to the desk? Because that's going to affect our normal force, Kendall.
Horizontal.
It was horizontal. That means it's not down or up. So in this case, these are the only two forces in the Y. So the normal force really will be, class, 147 newtons. Now, it tells us that the applied force here was what, Kendall?
55.
And so the only other force in play, class, is friction, which if he's trying to go that way with the applied force, friction would go this way. If he were trying to go that way, friction would go the other way, right? And to find friction force, we always do the same thing, class. We multiply the coefficient times the normal force. The normal force is that key. So we're going to take the 147 newtons, multiply it by the 0.341 coefficient to get how much friction force, Kendall?
50.127.
All right, so here's the question. Who wins, friction or applied force, class?
Applied force.
Applied force. Not by much, but it does win out. So here's the question. What is the resultant force, or the sum of the forces in the X, Kendall? Ooh, we did not find that then. Okay, seen a couple of you reaching for calculators. Michael, what did you have?
4.873.
Good. Ladies, confirm once you've got it. 4.873 newtons. And we've got to find that sum of the forces in the X, because if in order to find acceleration, class, we're going to use our basic equation, F equals ma, we're going to divide force by mass. But it's not this force, because there isn't a net force of 55. The net force is only this. We're going to divide that by the 15 kilograms to get our acceleration. And so, when you take what you have on the calculator, ladies, divide it by the 15 kilograms, hopefully you'll get what Michael got for his acceleration.
0.325 meters per second squared.
Good, 0.3248, blah, 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 rounded 3 sig figs, 0.325 meters per second squared. Ladies, do you have that now? All right? Any questions on how to find the acceleration of the desk? Again, what if friction had been greater? Does that mean the desk goes backward? No, it just means he doesn't move the desk. Okay, so if he's trying to push the desk that way or drag the desk that way, and there's more friction, it just means he's not moving the desk. It doesn't actually accelerate backward or anything like that. Any questions on this first problem? Let's take a look at the other problem that was on your handout, and it's the exact same problem, except same man, same desk, same amount of force, but now his force is not horizontal. What's he doing instead this time? Audrey?
He's angling it at 40 degrees.
He's pushing the desk, but instead of pushing horizontal or dragging horizontal, he's pushing with his arms at an angle of 40. So is he pushing forward, or is he pushing up, or is he pushing down? He's pushing two of those. Which one's, class? down and forward, right? So we're gonna have to change up our free body diagram just a little bit here. I'm gonna have the force approach, let's see. Audrey, do you want him to push it toward the screen or away from the screen? Away from the screen. So we're gonna have him come this way, and he's gonna push this way. And there's the actual applied force, the 55.0 newtons. But his arms make a 40-degree angle to the horizontal. So some of his force is down, some of his force is forward. Does that make sense? Which means if we're going this way now, friction is here. Now, the normal force is no longer going to be 147. Why not, class?
The applied force changes it.
Because the applied force bears not just forward, but now down, adding to the weight, right? There are now two downward forces. The normal force is your equilibrant. It's got to cancel these other two. So we got to, first of all, now again, the 40 is down in this corner. This is the opposite. So I'm going to use what trig function here? The sine, the opposite over hypotenuse. So we should take the sine of the 40 times the 55. How much downward applied force do we get, anyone?
35.
How many got the 35.35 downward? Perfect. Okay, then we also need to find the applied force forward using the cosine, because this is adjacent to the 40. There's your hypotenuse. How much forward force, class?
42.13.
All right, how many got the 42.134? So we're good with the two components. Excellent. Now, I'll go white here. We've got 35.35 newtons down, plus we have 147 newtons down. How many total down newtons is that, class? It's about 170, 180-ish, right? What would we do to find that number? Just add them together. But whatever that adds up to, this one force has to counter them both. So how much normal force should we have now? 182.35, da da da. Did we get that for the updated normal force? Okay, you two did. Does it make sense now? All right, and once we know the normal force, we can find the friction force. You're going to take your normal times the same coefficient of friction, 0.341. Now, how much friction force is there?
62.182.
I got 62.182, blah, blah, blah. Is that what you said? My brain heard 63, my ears heard 63. All right, Kendall's recalculating. Audrey is calculating. Did you already do the calculation?
No.
So you're going to take your normal force, right? Because friction is coefficient times normal force. So take your coefficient of friction times the normal force that was on your calculator. You should get 62.182. Now here's the question. I've got two horizontal forces. It's not 55 newtons pushing forward now. It's only 42.13. Resisting the 42.13 is 62.182. Who wins?
Friction.
Friction. So what's the acceleration of the desk? 0. There is no acceleration in the desk. Now, I should quantify again. Friction is up to 62.182 newtons of resistance, right? So it's not that friction like overmatches and the desk starts sliding out, because friction only resists. It does not cause. It resists with up to 62 newtons of force. Not that many newtons were applied. Acceleration is 0 meters per second squared, because you don't budge the desk. Does that make sense? Questions on that? That assumes a stationary desk, I should say. Questions on that? All right. So evidently then, if he's going to push like this, 55 newtons isn't enough. So let's do the exact same problem again, except now he's like, well, I am not losing no stinking friction force. And so Mr. Applied Force himself ups the ante to 200 newtons. Let's find how much of that is in the X and how much of that is in the Y. how much of it is downward, class?
120.
I got 128.5, blah, blah, blah. Okay, what's that going to affect? The normal force, right? That normal force is changing. So, because we've got to take these, the 128 down, plus the 147 down, the normal force has to counter both of those. How much normal force we got now? Ooh.
275.
So I think you were giving me, no, you weren't giving that to me.
She was giving me the horizontal force.
Oh, okay, sorry, yeah. So I was just looking for the normal force. It's going to be these two downward combined. 128 and a half, 147 comes to 275.5, blah, blah, blah. Yeah, upward. And if the normal force changes, class, that also changes the friction force. So we're going to take, and maybe that's the answer Audrey was giving me a second ago, we're going to take this normal force times the coefficient to get how much friction force?
93.2651.
All right, do we get that? Do we see the progression? Now, notice by pushing harder, all he did was increase the friction force, right? But he did also increase his own forward force as well. I'm going to put this in the memory of my calculator. And I'm going to go back now. I'm going to find how much applied force is in the X. You may have already done this. I had not yet. And that's your answer, Audrey, is what you called out a minute ago. How much forward force was there in the X? You called it out a second ago. Yeah, 153.2, blah, blah, blah. We have that. Now, there's only 93 newtons resisting him in the X. He's got 153 in the X. What am I going to do with these two values, class? Subtract. They're going in opposite directions. So I'm going to subtract the memory value. And what is then the sum of the forces in the X?
59.24.
He wins by 59.24 newtons. He ain't losing no stinking friction. And if that's the sum of the forces in the X, it's only a 15 kilogram desk still this whole time. So he's got some good acceleration going now. He's mad that he lost in the last round. 3.949 or rounded 3.95 meters per second squared. That's pretty good acceleration. Questions on this? Do we see the progression? All right, let's change gears just a little bit here. Take a moment to set up the free body diagram there at your seats. Just a moment to set up that free body diagram. How'd your free body diagrams look? Good to go? Obviously, you could have had her pulling this way, but we had a 32-degree upward force, friction going whatever, the opposite direction, and with normal force and weight. All right, continue working. Check your various forces. Check your components first. Did you get 38.16 forward, 23.84 upward? So on which one? Both of them?
No, I'm actually looking at different numbers. Never mind. I'm good on this.
Okay, so you're good on these two numbers. All right, did we find the weight to be 212.66? All right, so does 21.7 times 9.8? Double check that.
You know what? I did 27.1 correctly.
Oh, instead of 21.7. Okay, so little as Dexia got you. All right. So then, what we should do is take whatever your weight was, and class, do we add or subtract this weight, this force in the y? This force right here. Does it add to the weight, or does it subtract from the weight?
Subtract.
It subtracts from the weight because they're in opposite directions. So the equilibrant only needs to be 188.81 of normal force. Did we get a smaller normal force than weight? Or was it small? I mean, I know the number here was wrong, so this number would be wrong, but was it smaller at least?
Yeah.
So you did the correct process, okay? And then we should take the normal force, class, multiply it by the coefficient of friction, and we should get 21.147. So when it all comes down to it, she's pulling forward. Is it a girl? Yeah. Let's say I thought it was a girl. The girl's pulling forward with 38.16. Friction resists with 21.147. Who wins? Girl wins. There we go. By how much?
17.015.
That's the resultant force right there. She wins by 17.015. And if that's the resultant force, class, if I divide that by the mass, which was 21.7 kilograms, I will get the acceleration. And how rapidly does said sled accelerate?
0.78.
And you're going 2 sig figs, 0.78 meters per second squared. Questions on this? Do we feel like we've got level ground, because we're about to go sloped, we feel like we've got level ground figured out? Any questions at all on that? All right, go and clear your desk except for a clean sheet of paper and a pencil and a calculator. Clean sheet of paper, pencil, calculator, and everything else away. Again, the key is to get all your concurrent forces marked, calculate all the concurrent forces, just be careful with your calculations. Find that net force, that resultant force, divide by mass, that'll give you the acceleration. All right, first last name at the top of your paper along with today's date. first and last name, along with today's date. And today is 11/1/22. 11/1/22. You may want to clear your calculators. They should already be in degree mode from the problems we were just doing. And this is quiz 12A. Quiz 12A. All right, let's take a look at the quiz together very quickly. Numbers 1 through 7, some different terminology. Write the term that's being described. And then there's one problem for you to solve. So you're going to want to set up the diagram and work it all out. Be careful with sig figs in your final answer and units in your final answer. All right, use that quiz copy as a cover sheet and you may begin. Just a couple more minutes to be finishing up. Collect those from you. Or if you're watching on YouTube and need a little bit more time, you can pause the video, but if you're taking it here at school, just another minute or two to be finishing. We're going to go ahead and move on. And so if you would, go and get your notes back out, and let's take a look now at what happens when the surface is angled. So let's take a look at angled surfaces now. And go ahead and read the problem out loud if you would for us, Michael.
A 17 kilogram box is slid up a ramp with a coefficient of friction at 0.325, angled at 25 degrees above the horizontal. If a force of 200 newtons is used to slide the box, find the acceleration of the box.
All right, so here's the key on the angled surface. You've got to think of this. If you were to stand, I'm going to go ahead and drag the camera back over here so I can draw things a little bit bigger. If you were to stand on something, where you put an object on a ramp, so we put a box on a ramp, what's going to happen if it's a really slick ramp? It's going to slide down because weight pulls it down, right? Wait a second, I thought weight pulled straight down. It does. But if you look, class, at this as being x, and this as being y, weight which pulls straight down also pulls into the ramp and pulls down the ramp. Does that make sense? Weight acting straight down is actually angled with respect to the surface. So what we're going to visualize here is our whole XY system tilts. And it's now weight that is the oddball. Does that make sense? So the weight is truly straight down. Some of it acts in what we now call the Y. That's what pulls into the ramp, right? For instance, if the ramp isn't very strong, ever walked on a ramp that starts to give underneath you and it's a little disconcerting? Anyone ever walk on an old ramp or something that rotted through and you went through the ramp, right? That's because there wasn't enough normal force to resist your weight in the Y. Some of the weight pulls straight into the ramp and is countered directly by normal force. These two will be equal. But then there's that weight that pulls down along our rotated x-axis as well. Does that make sense? And this is the component of the weight that causes the box to slide. Does that make sense? So that's what we're going to have to do. Now, remember we talked about the principle of transmissibility. I can put this vector anywhere I want, and where I want to put it is right here. I don't actually want to draw it up here. Why? Because if I put the force of weight in the x here, I get this nice little right angle, which gives me my right triangle, where the weight itself is the hypotenuse. Now, the next thing I want to point out is this. A ramp, the whole premise of a ramp is that it's angled a little bit, correct? And we'll generally look at it as how much is it angled with respect to the horizontal, right? I want you to consider for a moment this angle right here. Do you notice that the y component is perpendicular to this? And you notice that the actual weight is perpendicular to this? Now go back in your mind to geometry class. This angle has a right side and a left side. This angle, as you look down, has a right side and a left side. You're looking down the angle right and left. Notice the sides are perpendicular, right side to right side and left side to left side. And if two angles have their sides perpendicular, right side to right side, left side to left side, Michael, the angles are equal. He's in geometry right now. Now, if you forgot that, it's okay. Here's what you're going to memorize. Whatever the angle of the ramp is, will be the angle between the y component that pulls into the ramp and the true weight that pulls straight downward. Does that make sense? So you don't have to remember the whole right, right, left, left thing if that confuses you, or maybe if you're watching on YouTube, you say, I never learned that principle in geometry. Don't worry about it. You just memorize whatever angle the ramp has will be this angle here. Now, the y is now my adjacent. So the y is going to use cosine. The x is now the opposite. The x is going to use sine. Do we understand how this free body diagram will work? Let's revisit the problem now then. Now that we've got this idea, and you're going to draw the free body diagram along with me. Here's the first strategy. Anytime there's a ramp or an angled surface, a sloped surface, start by drawing the sloped surface. So I'm going to start by drawing, okay, this would be horizontal, but it isn't horizontal. Instead, we have a 25-degree angle. So start by getting your sloped surface. Then draw the object as a dot or a box. And you can tell I'm partial to the box because I like to write what inside the box? The mass. There's really nowhere else to put it, so I'll put it there. It's a 17-kilogram box. Now then, you've got to solve the weight. Remember, the weight acts straight down. What is the weight, class?
166.6.
It's 166.6 newtons. We're thankful for that one. And the point. All right, now, that's the actual weight. Some of that weight, class, pulls it into the ramp. We call that the weight in the y. Some of that weight is trying to pull it down the ramp. We call that the weight in the x. So far, so good? Realize this angle at the top is the same 25 degrees. At your seats, how much weight pulls this box into the ramp? Call it when you've got it. How much of the weight pulls it into the ramp? Weight in the y. 150.99. Again, we're using what trig function here, class? Cosine. Because the weight in the y is adjacent to the angle, and we know the hypotenuse. Remember, we have this little right angle here. So the 166 is the hypotenuse. The weight in the y is the adjacent leg. So far, so good? Now, find the weight in the x. Oh, I'm going to put that in memory, by the way. How much weight pulls it down the ramp, class?
70.40.
All right, again, that's the opposite. Here's your hypotenuse, there's the 25-degree angle. So we use the sine. Are we good on the two components? Now, weight pulls down, both down the ramp and into the ramp. But it doesn't go into the ramp in this problem. It doesn't fall through because pushing upward perpendicular to the surface, class, we have the normal force. And the normal force will equal this weight in the y unless there was some other angled force. But here's what we're going to do. You're in high school, not college. Either the surface is angled or the force is angled. I'm not going to do both at the same time. So maybe college level you would. In high school, whatever the weight in the y is what your normal force is going to be. So we've got 150.99 newtons, still memory one, of normal force. Does that make sense? And the only reason we need the normal force class is so we can find the
Friction.
friction force. Now, which direction is the box being moved?
Up.
Up the ramp, which means friction class acts down the ramp. It goes against the motion. If the box were just sitting there, nobody was pushing on it, which direction would friction act? Up the ramp, because the weight in the X is already going down. Do you see that? If nobody touches the box, since weight in the X is pulling, remember I said on a really slippery ramp, it would slide down? Well, if it's not a slippery ramp, if there's friction, friction acts up to counter this. But if someone is pushing up the ramp, both of them are working together to stop you. So when you try to slide something up a ramp, it's like, man, it feels like everything's against me. Yeah, pretty much is. Not just friction, but the weight component in the X as well. Let's go get the friction force. Remember, that's coefficient times this normal force. So the 0.325 is the coefficient times that recall 1. How much friction is there, class?
49.
All right? Now, that's acting down because somebody is trying to push this thing up, correct? We'll assume it's being pushed straight up the ramp. Okay, we're not going to assume it's an angled applied force. That starts to get messy. The force is 200 newtons. But that's not how much force moves the box. Because working against the 200 newtons class, we have the 49, and we have, so the key thing to remember here is there's two forces that have to be subtracted away from the 200. So question, what is the net force? What is the sum of the forces in the X here? Perfect, 80.519 blah, blah, blah newtons. And if we want to find acceleration class, we divide the resultant force or the net force by the mass, which was 17 kilograms. And how rapidly does this box accelerate up the ramp?
4.74 meters.
Which is pretty good. By the way, if there's no applied force, remember we said the friction would act up the ramp? Who would win, friction or weight in the X, if friction were acting up the ramp? Weight in the X would win, right? So apparently this box would begin to slowly slide down if nobody were touching it, if nobody were pushing on it, right? Weight in the X would win out over the friction. It would still slide down the ramp. Rounded off, it's 3 sig figs, I believe, so we'll say approximately 4.74 meters per second squared. Questions on this? I'm going to have you try a problem tonight for homework. If you struggle, don't worry about it too much, but I want you to give it a try because I think it'll help to cement some of these ideas. You're going to read over pages 136 to 141, read pages 136 to 141, and then on page 142, I want you to do problem 9. Again, do your best. Get as many of these as you can. If you want to go back and rewatch the video, you can. I'm not going to require it, but do your best. See if you can figure it out. If not, tomorrow we'll be practicing a lot of these and should be able to clear up any confusion you have. Does you feel like it makes sense, though, where you're at right now? The key is getting that weight split into some of it down the ramp and some of it into the ramp. All right? We'll take a look at that tomorrow. We'll also look at your quizzes tomorrow. Have a wonderful rest of your day. You are dismissed.